Good morning.
Good morning.
Morning.
All right.
Mr. Strong in Winslow, the camera's still not fixed, so just a heads up.
Oh, dang. Okay. So did you try whatever you did last week? Because I thought you fixed
Of course I did.
it. So, oh, that's too bad. Okay, well, so I can see really fuzzy people close up. So, all right. Well, thank you. Yeah. So, yeah, just let them know, and then maybe after my class they can reboot it. Is usually what they do when it's on our end. So, all right. Well, thanks. Well, let's see who's here. And now I really can't tell it in Winslow, but all right. Rex,
Here.
Alana,
Here.
Diana,
Here.
Taylor,
Here.
Auburn,
Here.
Cameron,
Here.
Andrew,
Here.
Chandon.
Not here.
All right. Thank you. Junior,
Here.
Caden,
Here.
Jordan,
Here.
Ellie,
Here.
Dominic,
Here.
Brooke.
Here.
All right. Thanks. So Shannon's the only one not here. Well, I hope you all had a good weekend. I'm sure it was better than mine. I got sick about halfway through Saturday and was just sick as a dog the whole rest of the weekend. So I am so glad to be in school today. I'm so glad to be teaching because I do not like being sick. It's no fun at all. So did anybody do anything amazing over the weekend? No? All right. Well, so I had written down that we were going over the last problem, and I want to make sure that we have the last problem on 8.1. So we'll take a look at that, and then we're going to go on to 8.2 today. So if it will wake up and get me there. Okay, so it was with Heron's formula, and I don't think we went over the answer to this. Okay, so let's start there, and then I guess we'll go to 8.2. So let me go ahead and have that loading up. Okay. All right. Okay. Let's change that. All right. Okay, so practice 3B is kind of where we were. It says use Heron's formula to find the area of a triangle where A is 5, B is 9, and C is 8, all units in centimeters. So with Heron's formula, the first thing you do is find the semi-perimeter, or half the perimeter. So we add up the sides, and we get 22, divide by 2, and we get 11. Okay? So that's the semi-perimeter. So then with Heron's formula, what we do is we do the square root of the semi-perimeter, 11, times 11 minus each side. So 11 minus 5, 11 minus 9, 11 minus 8. Now you can simplify and then put it in the calculator, or you could just put it in the calculator just like that. Okay? But let's have you put that in your calculator if you haven't already, and just to make sure that we're okay with that. All those parentheses, sometimes it can be a little crazy. All right, so Cameron, what'd you get?
6 square root of 11.
Okay. So 6 square root of 11 is the exact answer, or if you approximate it, and I like that answer just fine. So let's write that 6 square root of 11. Or as a decimal, that would be 19.900. And the units for area are squared. Okay, so there's going to be squared centimeters on this one since it's area. All right. So anyone have any questions on that? All right. Does anyone have any questions there on 8.1? Anything on the sheet that you'd like me to go over? Or any problems you've been working on that you'd like me to review? Okay. Well, so today we're going to start on 8.2. And so remember the plan. So this week we're going to try to get at the very least through 8.3. Next week is spring break. Then the following week is when we have our midterm. And so you'll have a substitute Monday and Tuesday, and then your midterm will be Wednesday and Thursday. Okay? Any questions on that? Okay. Let's go ahead and get started. On 8.2, I did send out the guided notes, but you don't have any guided notes yet for the rest of chapter 8. So that's going to be forthcoming. All right, but if you have, does everybody have the 8.2 guided notes? Holbrook, Joe City, do you guys have them? No?
Miss Buckley isn't here today.
Okay. See, I sent those last week. I guess I need to ask her to maybe print them out ahead of time. Let's see, I'm trying to think. They might be, are they posted on the Moodle? They might be on the Moodle, in which case maybe you could send them to the library and, do it that way. Otherwise, you can just write stuff down and transfer it, But anyway, I appreciate you letting me know, because I'll go to the practice problems and stuff, so knowing that you don't have it in front of you. Okay, so section 8.2 is on polar coordinates and polar equations. And so this is a section that, again, depending on your Algebra 2 teacher, you might, there's a lot of you that might not have ever seen this before. Okay, so I'm going to teach it as if it's brand new to everyone. And if you've done it before, that's great. So we're going to talk about what the polar coordinate system is, and then how to convert back and forth between our normal rectangular system, is what we call it, the XY axis, and the polar system, and then the form of polar equations, and then graphing polar equations. All right, so this is what a graph looks like in polar coordinates. And so, you know, you might have seen this, like if you watch like a war movie, and usually like in a battleship or a submarine or something like that, they'll have a tabletop that looks like this. Because in the military, they often use polar coordinates for targeting, okay? Because everything is based on the center of your vessel right here. So, like the captain will say, okay, set a torpedo at a bearing of 45 degrees, so that's like your angle. And then the range would be 3 miles or something like that. And so this is what a polar coordinate looks like. So it's not an XY value, it's a range and an angle. Okay? So you go up 45 degrees and then you go out 1, 2, 3 circles, 3 radii. So the center point is called the pole. So like the North Pole. And then the positive x-axis is the polar axis. All right, so the polar coordinate system serves as a means of locating points in a plane. Instead of x, y, points are in the form r, comma, theta. So the radius and then the angle that it makes from that positive pole, that polar axis, the positive x-axis. All right, so if I were going to graph these, okay, so let's say the first one is 3.5 comma pi. All right, so you do the angle first, so pi would be over here, and then you go out 3.5, so that would be 1, 2, 3.5 would be right about there. All right, the next one, -2 pi thirds. So pi thirds, that's the same as 60 degrees. Now, by the way, for your own graph, you can just, if you just Google polar graph, then you can, you know, download these and print them off just to do your own graphs. And there's different ones where each one will be 15 degrees or 10 degrees or 45 degrees, whatever. But it just helps you find, so this is 60 degrees, okay, or pi thirds. But now, when it's -2, see the distance, it's like, okay, so I need to go, instead of +2, -2 is backwards. So along this line, you go backwards 2, and so that would be that point, okay? Then the third one, 300. So see, the angle can be in degrees or radians. So you give your 300 degrees is over here, and then you go out 3, 1, 2, 3, and so that would be your point there. All right. All right, so see if you can do this practice 1 here. See if you can graph those. And so we're just doing kind of a rough graph. So you guys that don't have the polar paper, it's okay. We're just estimating. So don't worry about being exact. Okay? Okay, so let's see. 3 pi fourths. That would be along this one. And then you go out 2, 1, 2. And so there's that one. 270 degrees, that's going down. So 3.5. So 1, 2, 3.5 would be about there. 4 pi thirds, let's see, pi is 180 degrees. And then you go another third right there. And so then, but -1, that means you're going backwards. So it's back up here in quadrant 1. All right, any questions at all on the points? Graphing the points. Okay, so now to convert from polar to Cartesian. So polar is the r theta. Cartesian's what we're normally used to, the xy points. Okay, or sometimes instead of Cartesian, it'll say rectangular. That's the system we normally have. But there's 2 equations that you need that will convert the polar to Cartesian, and that is x equals r cosine theta and y equals r sine theta. All right, so let's look at this example here. It says convert the following point from polar to Cartesian coordinates. So 2 negative pi thirds. So the 2 is what you're going to plug in for the r, and then the theta you're going to plug in negative pi thirds. So the x value is 2 cosine negative pi thirds. Well, the cosine of negative pi thirds, you can look on your unit circle, that's 1/2. So 2 times 1/2 is 1. So the x value would be 1. All right, to get the y value, it's 2 times the sine of negative pi thirds, which is negative radical 3 over 2. Again, from your unit circle. So now you divide, cancel the 2's, and so your answer, the y value would just be negative radical 3. So then your final answer then, the xy is 1 comma negative radical 3. So this is what we started with in polar form. This is the same point in rectangular form or Cartesian form. All right, any questions? All right, let's see. Negative 3 pi-4ths. Okay, here we go. So go ahead and try that practice problem there. All right, so Junior, when you've got the x value, let us know what that is.
Negative 3 square root 2 over 2.
Negative 3 times square root of 2 over 2. All right, good. Any questions on that? All right, so Andrew, when you have the y value, let us know.
Negative 3 square root of 2 over 2.
That's right. See, since the sine and the cosine of pi-4ths are the same, the x and y values are also going to be the same. Okay? All right, good job. Any questions on that one? All right. All right, next. Converting Cartesian to polar. Okay. Now there's two equations. R squared equals x squared plus y squared. And then okay, this is the formula that the book gives you. Tan theta equals y over x, where theta is a reference angle. So I just kind of write it like this. Theta prime, and the prime, remember, was how we wrote reference angles, is the inverse tangent of y over x. So to me, I like my formula better because it's, one extra step that's already done for you. Okay, so let's give you an example here. So now we're going to come back the other way. So we have our Cartesian, our xy point, negative 3, 2. And so we need to figure out the r and the theta to put it in polar form. All right, so first we use that first equation, r squared equals x squared plus y squared. So we say negative 3 squared plus 2 squared. So r squared is 9 plus 4, or 13. So r is plus or minus radical 13. Now, it turns out because the way you do angles, you could actually have it be plus or minus. But it's actually easier, at least for now, we're just going to say radical 13. Okay? And then we'll come back to the plus or minus thing. All right, so that's the r. Now, the theta is going to be, okay, so I'm going to just use this formula right here, okay? So theta prime is the inverse tangent of y over x, so negative 2 over 3. And so you can just put that in the calculator because that's not one that's going to be on the unit circle. So you get theta prime is negative 33.690. Okay. All right, now, here's the part where you have to use a little deductive reasoning. So you have to make sure that you're in the right quadrant. Okay? So let's look at our original point. Our original point is negative 3, 2. So that's in quadrant 2. Negative 33 would take us to quadrant 4. So if we're going to use that angle, then what we need to do is go backwards and change our r to a negative. Okay? So we could say use the negative angle and then use the r as the negative. Or we could say, all right, if I want to use the positive value, okay, of positive radical 13, then I say, well, I actually need to be in quadrant 2. So if negative 33 is my reference angle, then I measure up 33.690 from 180, or subtract, and I get that angle. And so this answer here in red is also correct. Okay? So that's kind of the only bad thing about polar coordinates, is that they're not unique. Like if on our XY plane, if I just punch any point, there's only one XY value. But in the polar coordinate system, there's actually many ways that you can represent a single point. Okay? So just know that here, so you could use the negative angle and go backwards on the r, or the positive angle and go up on the r, go positive on the r. All right? So let's see if you can do practice 2B. Let me go to that. All right, so Caden, when you've got the R.
For r, I got radical 2.
Okay. Actually, it should just be 2. Here, let's clean this up a little bit. Okay. So you get So r squared equals x squared plus y squared. So it's radical 3 squared plus negative 1 squared. So r squared equals 3 plus 1. R squared equals 4. So r would be either plus or minus 2. But we'll just go ahead and use the positive value for now. But it could be positive or negative depending on which way we need to go. Okay? All right, so Caden, what is the theta when you get it?
Is it negative 1 over radical 3?
Okay, so, well, we want the inverse tangent of that. Negative 1 over radical 3 is y over x. So what angle has a tangent of negative 1 over radical 3? That one would be on the unit circle. It would be, look on the unit circle for where the y is negative 1/2 and the x is radical 3 over 2. And then the 2's would cancel. So do you see that on the unit circle?
4 pi thirds.
Okay. It's actually would be 5 pi 6. 5 pi 6. Or negative 30. Okay. So then just so far our answer then would be r is 2, negative 30. But we got to make sure we're in the right quadrant. Because negative 30 and then out 2, that would be quadrant 4. So let's see. Is this radical 3, negative 1, is that in quadrant 4? Well, yeah. Radical 3, negative 1. So that would be our answer. All right. Any questions on that? All right. So to rewrite an equation in polar form, you use the formulas, the same formulas that we use for coordinate conversion. So the x squared plus y squared equals r squared, those two. All right, so these formulas right here. All right, so let's say I want to write this in polar form. Okay, now the easiest way to do it is look to see if you have an x squared plus a y squared. Okay, if you have an x squared plus a y squared, just substitute in r squared for that. That's the easiest way. All right, and then minus 2x. So then in place of x, you substitute in r cosine theta. So then your answer is r squared minus 2 r cosine theta equals 0. And that's it. That's the answer. So you just do 2 substitutions there and you've got it. Okay? All right, so go ahead and try practice 3A. All right, so Dominic, when you've got it.
I got r squared equals r cosine theta plus sine theta.
Okay, it's actually easier than that. See how x squared plus y squared, if you just substitute, see, this is like the long way to do it. If you just think x squared plus y squared is r squared, and then you just get r squared equals 81. And that's it. So you don't have to do the cosine and the sine. You could if but it's way more work. Okay? So just substitute x squared plus y squared is r squared. So r squared is 81. Now, you could even say r, if you took the square root, r is equal to 9. So what would that look like? Well, that would be a circle of radius 9. So you count over 9, and that would be what the graph would look like. Because it's saying, and you might remember from geometry that x squared plus y squared, that's the form of a circle. And so this is another way to express it, a circle of radius 9. Okay. Okay, so if a polar equation is not in terms of sine or cosine, rewrite the trig functions. Because we have r equals, x equals r cosine theta and y equals r sine theta. So if they're not in terms of sines and cosines, you're in trouble. You gotta do something. You gotta put it in terms of sines and cosines. Okay? So let me give you an example. So rewrite the equation 2r equals secant theta in rectangular form. Well, see, the problem is that we don't have a conversion to secant. So what you do is you say, well, secant is 1 over the cosine. Okay? And now you multiply each side by cosine. And so then this will cancel, leaving you with 1 equals 2r cosine theta. And then you say, okay, wait a second. What's r cosine theta? That's just x. So 2x equals 1. And then if you solve that for x, you'd get x equals 1/2. So you have to put it in terms of sines and cosines because we have that, that formula, the r cosine theta is just x. Okay? All right, so let's see if you can do that. All right, so try this one. So rewrite r equals 7 secant theta in rectangular form. All right, so Dominic, when you've got it. Now, because this is, might be new to some of you, I mean, I don't think these problems are all that difficult, but you definitely need to practice. So make sure you're doing some of the practice problems in the book and just checking them to make sure you're getting it down. All right, so Dominic, you have an answer? Or do you need some help?
I got confused after I got 7 cosine theta equals 1.
Okay, so you rewrite secant as 1 over the cosine. Then you multiply each side by cosine, and so you get r cosine theta equals 7. Now the 7 stays over there, it doesn't go anywhere. And then r cosine theta, what does that equal to? X. So the answer is just x equals 7. So when you're not moving the 7 at all in this one.
So do you not have to worry about the y?
No. Just like if an equation, like x equals 3, that's an okay equation of a line. It's a vertical line. So that's just the equation of it. Now, if it were, instead of secant, if it were cosecant, then you get y equals 7. Because then you get r sine theta. So,
Okay.
but yeah, so like for an equation of a line, it's okay if you don't have a y in there. Okay? Thank you for that question. Any other questions? All right. Okay, so now we're going to talk about graphing polar equations. To graph polar equations, remember r is the radius or the distance from the pole, from the center, and theta is the angle up from the polar axis. All right, so like if I wanted to graph r equals 6, that would be all of the points that were at a radius of 6. And so that would be a circle. So anytime your equation is r equals something, that's going to be a circle. So all the points have a radius of 6. It doesn't give us an angle. So all of them would be included. Okay? So what about the other way? What if I give you an angle but don't give you a radius?
And it would just be an angle at 120 degrees, like a line.
Okay, and then what did you say? After that, an angle at 120 degrees and
Just a line.
a line. Yeah, that's what the word I was looking for. So it's going to be a line because it's going to be all of the radii. So you measure 120 degrees, and then it's all the radii, all of the distances. So it would be a line. Great job. Okay. Any questions on that? All right. So the most basic approach to sketching the graph of a polar equation is to plot some points. Okay. Now, here's the deal though, is that plotting points can sometimes take a long time. I want you to know how to do it, but typically when we do these for real, we're going to put them in the calculator. Okay. So I'm going to show you how to plot points first, and then I'm going to show you how to put it in the calculator. All right. So let's say we wanted 2 cosine theta. Now, because we're going to be doing these in the calculator, in which you want to be in radians, it usually, when I do the graphs in radians too, but you could still have your angles in degrees if you want. All right, so you say, okay, so you're just plotting points. So you say, just pick your normal angles, okay? 0, pi 6, pi 4, pi thirds, pi halves, and pi. So the cosine of 0 is 1 times 2 is 2. Cosine of pi 6 is radical 3 over 2 times 2 is radical 3. The cosine of pi 4 is radical 2 over 2 times 2 is just radical 2. Anyway, you go through and then you just get these points. And so then you say, all right, so 0, 2. So here's the angle is 0, and then you come out 1, 2. Then the next angle is pi 6, and you're coming out radical 3, which is 1, and then a little bit more than halfway, 1.7. And then for pi fourths, let's see, right here, it's radical 2, which is 1.4, approximately. And then for pi thirds, we have 1. For pi halves, we have 0, and so on. And then you can, your other angles around here, you can get as many points as we need. And so it kind of looks like this little green shape here. Okay. All right. So if we were to graph this, though, in the calculator, 3 sine theta, okay? So we could make the table just like I did before. And here we did it in degrees just because we can. But what I want to really show you here in this practice problem is how to put it in your calculator. So grab your calculators. Okay, So to put it in the calculator, it's 3 sine theta. To put it in polar form, you have to change the mode. Okay? So if you press the mode button, and so I'm going to change it to radians. Oops. And then, see, normally we graph functions, but now we're going to graph it in polar mode. So from function, you got to arrow over to polar, and then press enter. And then when you press the y equals, you'll notice that instead of saying y equals, it actually says r equals. Because that's the form of a polar equation. So we just type in 3 sine theta. And so in polar mode, the variable key comes up as theta. So 3 sine theta, and then press graph, and then press graph, and then boom. All right, anyone having any trouble getting this graph to show on the calculator? I can go through it again if I need to. All right, now, the next thing we want to talk about is symmetry. Polar equations often are symmetrical. This one is symmetrical about the y-axis. But we don't call that the y-axis in polar equations. That's pi equals, or theta equals pi halves would be that y-axis. So when we talk about symmetry of polar equations, okay, there's symmetry through the pole, or what we normally think of as the origin. And so those are ones where if you turn it upside down and you get the same graph, it's symmetrical through the pole. All right, then you have symmetry through the polar axis, where if you fold the paper along the positive x-axis and one side is the mirror image of the other, then it's symmetrical along the polar axis. And then the one that we just did, symmetry through the line theta equals pi halves, that's like symmetry along the y-axis in Cartesian. All right. There's also different kinds of polar equation graphs that we'll refer to. All right. The first ones that we've done are circles. So circles and spirals. Then we have what we call limacons. And I think of these looking like lima beans. That helps me remember lima. And then the flower looking ones we call roses. And then the last one are called lemniscates. And I remember that by figure 8 lemniscate. If it looks like a figure 8, then that's called a lemniscate. So tomorrow we'll go through part 5. And we'll graph it and talk about the symmetry and what type